this episode, we take the stability problem you learned about with decision trees and solve it in a very practical way by using ensembles, which are models that combine many simpler models to get a stronger result. Random forests and bagging are two closely related ensemble ideas that are widely used because they can take a high-variance learner like a decision tree and make it far more reliable. Beginners sometimes think an ensemble is just a fancy trick to boost accuracy, but the deeper purpose is robustness, meaning the model behaves more consistently when data is noisy, when the dataset changes slightly, or when there are many features that provide competing signals. The key concept is variance reduction, which means reducing how much the model's learned structure changes when the training data changes. Decision trees can swing wildly because they are sensitive to small differences, and ensembles address that by averaging across many trees so that quirks cancel out and stable patterns remain. The goal here is to understand what bagging is, what makes a random forest different, and why these methods often produce better generalization without requiring you to perfectly tune a single tree. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at Cyber.Author.me in the Bare Metal Study Guide series. Bagging is short for bootstrap aggregating, and while the name sounds complex, the idea is straightforward. You create many different training sets by sampling from your original dataset with replacement, meaning the same example can appear multiple times in a sample, and some examples will be left out. Each sampled dataset is called a bootstrap sample, and it is roughly the same size as the original dataset. Then you train a separate decision tree on each bootstrap sample. Because each tree sees a slightly different view of the data, the trees will not be identical, even if you use the same training settings. Once you have many trees, you combine their predictions, usually by majority vote for classification or averaging for regression. This aggregation smooths out the instability of any single tree, because a noisy split that appears in one tree may not appear in others, and the vote tends to favor patterns that show up consistently. The result is a model that is less likely to overreact to noise and less likely to produce wildly different outputs when retrained. The reason bagging works so well for trees is tied to how trees fail. Trees are flexible, and that flexibility is what makes them high variance, meaning they can fit random quirks in the sample. High-variance models benefit from averaging because the average of many noisy estimators can be much more stable than any one estimator. If each tree makes errors in different places, the averaging can cancel those errors, improving performance. This is similar to how taking the average of several noisy measurements can give you a better estimate than relying on a single measurement. However, for averaging to be effective, the individual trees must not all make the same errors in the same way. If the trees are too similar, then averaging does not reduce variance much because the errors are correlated. That leads to the next idea, making trees diverse, which is where random forests add a key twist. A random forest is essentially bagging plus an additional source of randomness that encourages diversity among trees. In bagging, trees differ because they see different bootstrap samples, but they can still end up choosing similar splits, especially when there are strong features that dominate the decision. Random forests reduce this domination by limiting the set of features a tree can consider at each split. Instead of examining all features, each split considers a random subset of features and chooses the best split among that subset. This forces different trees to explore different feature pathways, which reduces correlation between trees and makes averaging more effective. In other words, random forests make trees disagree in useful ways, so their average is stronger. This is why random forests often outperform plain bagging when there are many features or when some features are very strong and would otherwise drive all trees towards similar structures. The combined effect is a robust model that generalizes well and is less sensitive to the quirks of any one tree. It helps to connect this to the bias-variance trade-off you have seen before. A single deep decision tree typically has low bias and high variance, meaning it can fit complex patterns but is unstable. Bagging and random forests primarily reduce variance while keeping bias relatively low, which often improves overall error. You can think of the ensemble as keeping the expressive power of trees, but smoothing out the randomness of the learned boundaries. In many practical problems, this is exactly what you want because data is messy and you need a model that does not overreact. However, the trade-off is that interpretability changes. A single small tree can be read as a set of rules, but a forest with hundreds of trees is not easily readable in that same way. You can still explain a forest at a higher level, such as which features tend to matter, but you cannot easily point to one path that defines the model's logic. So the model becomes more robust, but less directly interpretable, and managing that expectation is part of using the method responsibly. Another important concept tied to bagging is out-of-bag evaluation, which is a clever way to estimate performance without needing a separate validation set. Because each tree is trained on a bootstrap sample, some examples from the original dataset are left out of that sample. Those left-out examples are called out-of-bag examples for that tree. You can use each tree to predict on its out-of-bag examples, and by aggregating these predictions across trees, you get a performance estimate based on data that was not used to train the predicting trees. Conceptually, this gives you a built-in reality check and can help detect overfitting. For beginners, the key takeaway is not the procedure, but the idea that bagging naturally creates internal holdout data, which can support more honest evaluation. This also illustrates the broader theme that good modeling includes reliable assessment, not just training. Even when you are not doing a full workflow, understanding where trustworthy evaluation signals come from helps you avoid being fooled by training performance. Random forests also provide feature importance summaries, which can be useful but must be interpreted carefully. Because trees split on features, you can measure how much a feature contributes to reducing impurity across the forest or how much prediction error increases when a feature is disrupted. These importance measures give a sense of which features the model relied on, but they are not the same as causal influence, and they can be biased by feature properties like scale, number of unique values, or correlation with other features. For example, if two features carry similar information, the forest may split importance between them or favor one due to subtle sampling effects. Beginners sometimes see a ranked feature list and treat it as a definitive statement of what matters, but it is better viewed as a model-specific summary of usage. It can guide investigation, help with feature selection, and help with communication, but it should be paired with deeper checks and domain understanding. In a certification context, the safe claim is that feature importance indicates which inputs were helpful to the model, not which inputs cause outcomes. Robustness is not only about average accuracy, it is also about how the model behaves in edge cases and underdrift. Random forests and bagging often handle noisy features and outliers better than a single tree because outlier-driven splits are less likely to dominate across many trees. They can also provide more stable predictions in regions where a single tree would create sharp boundaries based on a few points. However, they are still trained on historical data and can struggle if the environment changes in a way that shifts the relationship between features and outcomes. Ensembles reduce variance related to sampling noise, but they do not eliminate bias from wrong assumptions or missing information. If your features do not capture the true drivers, a random forest cannot invent them, and it may instead learn proxies that work temporarily but fail when conditions change. This is why monitoring and validation remain important even for robust models. For beginners, the key is to see robustness as resistance to overfitting and noise, not as immunity to real-world change. Choosing how many trees to include is another decision that affects performance and practicality. In general, adding more trees tends to improve stability because averaging becomes more effective, but the improvement eventually levels off. More trees also mean more computation and memory, especially at prediction time. The important conceptual takeaway is that random forests reduce variance by averaging, and averaging gets better as you include more diverse estimators, up to the point where additional estimators add little new information. The diversity comes from both bootstrap sampling and feature subsampling. So if trees are not sufficiently diverse, more trees will not help much. Conversely, if trees are diverse, you may achieve strong performance with a manageable number. As a beginner, you do not need to memorize specific counts, but you should understand the direction. More trees usually means more stable, and feature randomness helps make those trees less correlated, improving the averaging benefit. There are also pitfalls to avoid so you do not overclaim what random forests and bagging provide. One pitfall is assuming that because the model is an ensemble, it is automatically fair, safe, or unbiased, which is not true. The model can still learn biased patterns present in the data, including proxies for sensitive attributes, and because it is powerful, it may learn them even more effectively. Another pitfall is confusing robustness with explainability, because while forests are often easier to use successfully than single trees, they can be harder to explain at the level of individual decisions. If stakeholders need a clear reason for each prediction, a forest may require additional explanation methods and careful communication of limits. Another pitfall is assuming that an ensemble solves data leakage or labeling issues. It does not. If training data contains leaked features or incorrect labels, the forest will happily learn them and may become confidently wrong in production. Using ensembles responsibly means keeping the same discipline about data quality and evaluation that you would use with any model. To bring it all together, bagging and random forests are about taking a model that is flexible but unstable and making it stable through averaging across many trained versions. Bagging creates diversity by training trees on bootstrapped samples and then aggregating their predictions, which reduces variance and improves generalization. Random forests add feature randomness at each split to make trees less correlated, which strengthens the averaging effect and often yields even better robustness. These methods often perform well with less delicate tuning than a single tree because they are naturally protected against some overfitting, but they still depend on good data, thoughtful evaluation, and realistic expectations. For the CompTIA Data AI certification, the key is being able to explain why a single tree can be high variance, why averaging reduces that variance, and why feature subsampling matters for diversity. When you can articulate those ideas, you are not just naming random forests and bagging. You are demonstrating that you understand the mechanism that makes them reliable.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.